Hi everybody, welcome back to our next topic in grade 12 physics. What we want to look at today is actually trying to explain something you've probably seen before. Um, Maybe you've even noticed it, and we just kind of want to see if we can explain what's going on, the physics behind it, and we're actually going to use it to further on our study of light. But what we're going to look at today is something called the diffraction of waves, and we'll also look at the interference of waves. And we're going to look mostly today at water waves, just because this is something you're a little more familiar with. Um, it's something quite visual, but later on we'll extend it to other kinds of waves. And if you remember your grade 11 stuff, you've done this already, maybe not diffraction, but you've done interference of waves certainly with sound waves. But today, again, we want to start with diffraction. And to give you an idea what that is, here's an overhead picture of, I guess it's like a harbor or something. And so what you're seeing is you're seeing some water waves coming in here. You can see the waves coming in from the ocean. They enter in through this kind of channel. So here's some rocks here and some rocks here. And you can see the waves change sort of their pattern when they go through this sort of channel. And then they spread out here and they do some funny sort of patterns. And again, our job today is to kind of explain what's going on there and look at what's happening. And as I said, we'll constrain ourselves today mostly to water waves, but later on we'll generalize this to all sorts of different kinds of waves. So let's start with kind of a description or definition of diffraction. So what diffraction is, it's just this process of a wave bending or spreading out when it either passes an obstacle or it goes through some sort of an opening. Um, so again, this is something you've experienced definitely with sounds. So if you imagine you can hear around corners, you can't really see around corners. So here's like this diagram here. So imagine Jill is talking inside of a classroom. You can't see Jill because there's a wall in the way, but if the door's open, you can hear Jill quite clearly because the sound waves that are coming off of Jill, they go through this doorway and they actually go through this process called diffraction, where once the waves come through the doorway, they start to spread out. And then you over here, I guess this is you, Jack, you hear the sound waves. And so then it's because diffraction has occurred. The waves have spread out as they go through this opening. But it doesn't have to just be an opening. So here's another picture of, let's say, water waves coming past an obstacle. They'll actually bend around the obstacle. You can see this sort of red line here showing that. And that process is also diffraction. And so this is actually pretty cool because all types of waves exhibit this behavior. Diffraction applies to all of them. So if you remember, we've been talking or going under the assumption that light behaves as a wave. So an obvious question might be, well, hold on a second, because sounds works as a wave, and you can hear around corners, and we're going to the assumption light works as a wave, but I can't see around corners. So clearly there's something that's going on here. And that's, again, part of the job we have today is to explain what the heck is going on. And it has to do with two big sort of dominant factors. There's two sorts of things that are going to make diffraction a bigger or smaller effect. Wavelength and the width of the opening. And so let's explain the effect first, and then we'll try and explain why that happens. So the wavelength actually has a big role. So generally, the longer the wave, the more diffraction occurs. So the wave that is longer, so these blue lines here, maybe I should just actually pause and explain these. These blue lines here, these would be the distant, or say the representation of, let's say, the crests of a wave. And the spaces in between would be the troughs of a wave. And so we're actually seeing like this wave front moving towards it. It would hit this barrier, and you can see the wave then spreads out. That's diffraction. And in the second example here, the waves are closer together. So in this example, the wavelength would be smaller. So we have a shorter wavelength. So in this example here, we have a, come on, over here we have a shorter wavelength. And so what we're actually happening then is we're having less diffraction happening. And we can see that because look how much this one spreads out compared to this one. This one doesn't spread out very much, where this one spreads out quite a bit. And this has to do with the fact that its wavelength is much longer and this wavelength is much shorter. So there's like the first sort of factor that affects it. The next really important one is the width of the opening. So how wide is it between this obstacle? So how big is the doorway? How big is the hole? Whatever case we're looking at here. And in general, the smaller the opening, the more the diffraction occurs. So if we have a very wide opening here, the diffraction is quite small, so there's not much sort of spreading that goes on here. But if we have a very narrow or tight passageway, then there'll be lots of diffraction that happens, so it's going to spread out quite a bit. So even though the wavelength in these two is the same, there's more diffraction, there's more spreading out in this case here. So generally, if we want to maximize diffraction, what we want to have then is a very wide or long wave and a very narrow opening, and that would have lots and lots of diffraction happening. So just to quickly summarize here, in order to get lots of diffraction to happen, we can actually kind of measure the amount of diffraction as this ratio, lambda over W. And again, if I go back up for a second, I said lambda is the wavelength and W is the width of the opening. So if I want to get lots of diffraction, I want to have this ratio be very high. And in general, I mean, this isn't a hard cutoff, but in general, if you want to have an observable sort of amount of diffraction, you want to see it happening or hear it happening or whatever the heck kind of wave it is, you want to have this ratio greater than 1. So that's kind of our cutoff. So if I want to have observable diffraction, I want to have the ratio of the wavelength to the width of the opening greater than or equal to 1. Or another way to write that is then to say that I want to have the wavelength. Ooh, let's try that again. The wavelength greater than or equal to the width. So if I have that, I'll have quite a bit of diffraction, something I should be able to notice or observe. And if I don't have the wavelength greater than or equal to the width, I'm not going to have a lot of diffraction. And so again, that's kind of our measuring ratio. So that's the effect and sort of what's going to affect it. But now we can figure out what sort of thing is causing it. And so we're going to go back to I think it's the 1600s actually, to this guy named Christian Huygens. And he worked with waves a lot, and he came up with something called Huygens principle. And he came up with this principle to explain lots of different behaviors of waves, and one of them has to do with diffraction. And again, we'll talk about this in just a second. But his principle, here it is. I'll read it out for you. Every point on a wavefront can be considered as a point source of tiny wavelets that spread out in front of the wave at the same speed as the wave itself. The surface envelope tangent to all the wavelets constitutes the new wavefront. So it's very wordy, and so what it really just says is that if we imagine here's the wavefront, so that's this dark line here at the front here, or this curved line here. What that is we can imagine that that wavefront is actually just a bunch of little tiny, what Huygens has called wavelets. These little tiny waves that are actually acting as their own sources. And when you add them all together, you're getting this nice, smooth wavefronts. And so that actually explains a lot of things, because then what that explains is in diffraction, if I have, let's say, an opening here between these two, as the waves are coming up, it's actually a bunch of little point waves. And so all the little sort of wave parts coming off of it are just going to start spreading out. And so it's going to spread out from that opening based on each little wavelet, as Huygens has called them. And so that explains diffraction quite nicely for us, and it certainly explains some other factors that we will come up upon a little bit later on. So that kind of explains the why of diffraction now. So let's do a quick little quiz here, quick check. 2 things I want you to think about. So when listening in on a conversation in another room through an open door, would it be easier to hear low-pitched or high-pitched voices, and why? And in order to observe diffraction with red lights, around what width opening is required? So approximately how wide would that opening need to be? So I'm going to have you pause the video there for a second. Think about questions 1 and 2. Come up with an answer for me, and when you think you've got one, restart the video. All right, so hopefully you've got for number 1 that it has to do with the wavelength here, because what makes a voice different from a low-pitched voice is the wavelength. Hopefully, again, you remember that from grade 11 physics. And so high-pitched means high frequency. So let's say high-pitched means high frequency. And so we have a high frequency. And what does that mean? Well, in terms of wavelength, what we remember the universal wave equation, V equals lambda F. So if V equals lambda F, what that means is if I have a high frequency, I'm going to have a low wavelength. So a high-pitched voice will have a short wavelength, And a low-pitched voice will have a long wavelength. So with that in mind, which one of these is going to have more diffraction? It will be the lower pitched voice. And so that means it will be easier to hear the person with a lower pitched voice because their voice will spread out more around the walls because their waves are longer. And so the answer, of course, would be the, oh, not the high pitched. I guess I shouldn't have written that because it looks like the answer now. The answer is actually the lower pitched voice, just because the waves are longer, and the longer the wave, the more the diffraction occurs. So the answer is a lower pitched voice. Great. All right, and again, I asked you for number 2 to think about that one as well, so hopefully you got an answer for that one. But if I want to observe diffraction with red light, around how wide does the opening need to be? 1 meter, 1 centimeter, a kilometer, how big? And so again, we go back to the idea that in order to observe diffraction, the ratio of lambda over W needs to be on the order of 1. Or what that means is that if I want to observe it, the width has to be where are we here? Less than or equal to the wavelength. So we need to figure out what the wavelength of red light is. The wavelength of red light, you can look that up if you don't know, but it's around 700 nanometers. So that means the width of this opening needs to be less than or equal to 700 nanometers, or that's written as 7 times 10 to the minus 7 meters. So that's an incredibly small opening, 10 to the minus 7 meters. So that kind of explains why we don't see diffraction in everyday life. When you open your front door, you don't see the light bend around corners just because the opening is way too wide. In order to have diffraction with light, you need very, very, very small openings. So if I can jump back for a second, that kind of answers our first sort of question that we started this class with is why can't we see around corners? Because our corners are much too wide open. We need to have much smaller openings in order to have light diffraction be really noticeable. Okay, so we've explained diffraction there. So let's jump now into interference. So again, this builds on some stuff you guys did in grade 11, so I'm going to very quickly just remind you of this principle of superposition. So superposition, all it says is when I have two waves that are overlapping, which means they're in the same spot at the same time, I add their amplitudes, and that principle is called superposition. And so we have two kind of basic possibilities. We have what's called constructive interference, where these two are in phase. So as this wave is up, the other wave is up, and so we end up with a big up. And conversely, when this one is down, so we end up with a big down. And so this wave ends up being twice the size of these waves. The opposite case is what's called destructive interference, and that's when this wave, the first wave is up, this wave is down, and vice versa. So we end up with no wave at all, and that's destructive interference. They're out by 180 degrees, or pi by 2, or pardon me, lambda by 2, or half a wavelength out of step. And so we have this destructive interference. All right, so why am I telling you this? Well, it has to do with what we're going on to next, which is this idea of diffraction and interference, what happens when these waves interact with each other. And so this is something kind of neat. And so let's take a look at this idea of waves interfering with each other. And so I have a little thing to look at here. So what I've got is a drop of water falling in a bucket, and you can see then the waves that are being produced by it. Let's actually increase the amplitude here. And so you can see the dark bands will be like, let's say, when the waves are down, and the bright bands, like this one here, will be when the waves are up. And I can make this wave more frequent. And you can see these nice defined bands, so the ups and the downs, the dark bands being the troughs, the bright bands being the crests. And so what I can do, though, is I can actually have two drips going at the same time. And if I have two drips going at the same time and I let them run for a minute, you can see something kind of neat. Look at sort of over on this side of the screen what you're seeing. If I just keep my mouse right there and I watch how does that change over time, it goes bright, dark, bright, dark, bright, dark, just like you'd expect it would. Expect it would. But if I go up a little further, that spot never changes. It's always just this dull gray. And if I bring this detector in, which shows me the height of the water wave at wherever my detector is, so let's put it here, right here, you can see it goes up and down just like you'd expect it to do. But if I move it over here to where it's nice and gray, it's still. That water is not moving up and down. We can ask ourselves, what the heck is going on here? And this is this pattern of interference. Um, that's as one wave is coming, the wave coming from this drip is meeting up with the wave coming from this strip. They're always out of phase. One is up while the other is down, always at this location. And so this wave will never go anywhere. But in the opposite spot, if I put it here, these waves are in phase. So they're both up at the same time, they're both down at the same time. And so the wave actually adds together. And if I turn one of these other ones off and let the wave actually reach there, watch what happens to the amplitude here. Once the other one goes away, it's now half as big because the wave is now only, it's only one wave as opposed to two. I turn it back on again, give it a second to catch up, and you'll see the amplitude will jump back up to where it was before. So this is again something kind of strange, but I have right here, I have two waves that add together. Let me actually find right the perfect spot where it's almost zero. I have two waves here that add together to make less, and if I turn one off entirely, that wave gets bigger. So adding two waves together makes the wave smaller, which seems kind of strange at first glance, but it does make sense when we think about it. All right, and one of the other neat things we can do, turn this guy off here, with even one faucet or one drip, one source, if I use this idea of a barrier or this slit, we can get the same sort of thing happening just because, according to Huygens' principle, each one of these slits or barriers acts as its own source of waves. So you can see again, there's that spot, that sort of line where you're not having any waves form. There's another one there, and you have these spots in between. Let me add the detector again so I can kind of show you. So there's like a grayed out area where the water is still, and then in between, there's a spot where the water goes up and down, and then there's a spot where the water's still, and then a spot where the water goes up and down. So I think that's pretty neat. We can show the same sort of effect either with two taps by themselves or with two slits. And one of the neat things, when we go back, turn this guy off and go back to the two drips, and I can see this pattern that develops. But one of the other neat things I can do is if I then make it so the frequency is different, what sort of pattern do you think would happen? So if I make this less frequent, watch how this pattern changes. That's maybe not frequent enough. You can't see the pattern now. Let me turn that back up a little bit here. So about half the frequency we were before. Let that develop. And hopefully what you can see is there is a pattern again, but it's different than it was before. So what does that tell you? It tells you that this pattern is actually dependent on the wavelength. And so there's wavelength dependent on this thing. So it actually depends on how long that wave is, where this pattern will be. Again, if I increase this frequency a whole lot, let's watch how the pattern changes now. You actually get way more of these um, dead zones. We're going to call these nodal lines, just like you called nodes and antinodes in grade 11. All right, so I think that's enough out of this for right now. So let's get rid of this. And what we need to do is try and explain what we saw. So what I've done, well, actually I've stolen this out of your textbook, but here's just a picture of what we've seen. So S1 and S2 are these are the two different sources. And these lines are kind of these well, I call them nodal and antinodal lines. So these are the spots where we're having constructive and destructive interference. So everywhere along these open circles, this is where the water was still. Everywhere along the dark circles, this is where the water was going up and down. And so we're having constructive interference here and destructive interference here. And our job now is to try and mathematically explain this. So I'm going to forewarn you, we have to get into some geometry, and certainly there's a little bit of algebra to get through. We'll get to the end results, and I'm going to try and make this as painless as possible, but just bear with me. Okay, so let's try and go through what's actually happening here then in terms of the math. So the first thing we want to do, let's consider the first nodal line. So we're going to call that, these spots where they have the open circles where the water isn't going up and down the nodal line, and we're going to pick any point on the first nodal line and call it P1. And so the first nodal line would be like this guy right here. So here's our first line. Let me label that. Let me draw a picture on here. So here's our first nodal line. This one right here, number 1. And we're going to pick any point on that line. So let's just say right here, right there, because I like that point. And I'm going to call that point. Where's my marker? Come on, wake up. There we go. I'm going to call that P1. All right. That's supposed to be a 1. There we go, great. All right, so I have P1, um, and I'm going to imagine that point there, and if it's on the nodal line, that means these waves must be out of phase. And that means they have to be out of step. But what's special about the first nodal line is that a wave that has traveled from this source, so it's gone from here to P1, has traveled, that's supposed to be a straight line, and a wave that has traveled from source 2 there, and I'm actually going to do this with straight lines, is actually out of step. So, so from source 1 to P1 and source 2 to P2, they're actually out of step by half a wavelength. They're half a wavelength out of phase. Source 2 has traveled half a wavelength further than source 1 has. So that means that source 2 is actually waves up when source 1's wave is down, and so this wave will be out of step. And anywhere along the first nodal line, that'll be true. And so that means that first nodal line will always have destructive interference. And I could have picked that P1 anywhere along this first nodal line. And the same is going to be true, or at least for the second nodal line, it'll be 3/2 wavelengths out of step. And for the fifth nodal line, third nodal line, it'll be 5/2. For the fourth nodal line, it'll be 5 or 7/2. And so you see the pattern here. We end up with this. And this is just our difference of path lengths. So we're going to call Pn, P being a point on the nth nodal line, and S1, S2 just being the distance from S1, source 1, and source 2, is given by this expression. So this is a fantastic expression, tells me what sort of wavelength do I need to get the nodal line there, or if I have the nodal line there, what wavelength would it require? So I can actually then figure out the wavelength of my source, or where would I have to be at a certain nodal line. So this is fantastic, but the problem is that if I actually want to deal with very small wavelengths, or if I want to be at points that are very far away, measuring these wavelengths or measuring the distance or the differences in these paths can be technically challenging. So we need another way to do it. So we can actually then go a little bit further and make some approximations. So this is true in general here, but if you make some approximations, and so what we're going to do is we're going to say, well, we're going to be really, really far away from these things. And if we do that, even though these nodal lines are not really lines, if we go far enough away, they become almost line-like, and it looks like they all start from the center of the sources, right here. And so if we make that sort of assumption, we can actually do a lot of kind of neat math tricks, and I'm not going to go through it all with you because I think it would take a long time and not be terribly useful for you. Or if you do want me to go through it with you, I'm more than happy to in class or after school or anything, so let me know. But you end up with this expression here. And what this expression actually tells you is how far away do you need to be from the center line. So if I imagine drawing, let me draw the center line here. I'll do it in red. So the center line is this red line here, goes straight up the middle. They call it the bisector because it's going straight through the center and straight up the middle. So at some distance away from the central, that's xn. They call it the right bisector. That red line is the right bisector. Let me draw an arrow there, maybe. Right bisector right there. So at any point Pn on the nth nodal line, let's say right here, so this would be our second nodal line now, we just measure the distance. So this tells me how far away do I have to be from this right bisector to be at a point on the nodal line. So this tells me where would the water be still, where would the sound be quiet, where would the light be dark. Some really cool things that, again, we'll look at when we go further on in lights. But it's based on, again, the wavelength of the light, D, and D is going to be, again, the separation between the sources. So S1 and S2 are separated by some distance D, and N is just the nodal line number. So starting from the center of the right bisector, counting out, N equals 1 would be your first nodal line, N equals 2 would be your second, N equals 3 would be your third. And so again, in my picture here, the red line is the right bisector, so this would be the N equals 1 case, this would be the N equals 2, this would be the N equals 3, this would be the N equals 4, and if there's another one, it'd be 5, and well, you get the idea. And so this actually then tells you where do you need to be in order to find this nodal line. And I think this is kind of neat. All right, so let's do a quick example. We'll go back to sound again for a second because this is something you're a little more familiar with. So you may have remember way back in grade 11, you probably did something like this in sound. If you had me for grade 11, you definitely did this. I set up some speakers and we wandered around the class and we found some spots that were quiet and some loud spots. But we didn't actually calculate where those spots were, but I think you were all thoroughly impressed, because I know I was, that we actually found some spots where the two speakers actually added together to make it quieter. And so what we're doing here is let's actually figure out, where do you have to stand? Where do you need to be in order to have a quiet spot? Um, and so we're going to make the approximation that we're far enough away and the wavelength is actually small enough so we can use this new expression that we just developed. And we want to figure out, where do we have to stand in order to not hear the sound from the speakers? So actually what I encourage you to do is pause the video, try this on your own, and when you think you've got an answer or you get really, really stuck, not just a little bit stuck, really, really stuck, start it up again and tell me, and then we'll see where we can go. All right, so you pause it, you try it, and when you're done or stuck, come back. All right, hopefully you didn't just lie, and hopefully you've got something for me. So we're going to start with the expression of x sub n over L equals n minus a half lambda over d. And we want to find, where does this gentleman or you need to stand? So how far away from this nodal line? So like, how far away does this need to be? And hopefully you can recognize this is xn. We want to know, where do you have to stand? So our 2.5 meters, that's going to be our d, because that's how far apart our speakers are from each other. So that's 2.5 meters. We know our wavelength, that's just given up by here, 0.15 meters. Our length is 20 meters. So the only thing we're really missing then is n. What the heck should we use for n? Because all we know is how far from the center of the room should we stand to not hear the sound from the speakers. And really, we have more than one option, because there should be more than one nodal line. I'm going to suggest, let's start with, well, actually, let's just do x1, and then we'll do x2 and x3 and see what we get. So now that we know the numbers, it's just a matter of rearranging. So again, I think you can probably do that, and hopefully you did. But for x equals 1, I'm getting 0.60 meters, so 60 centimeters. So what that means is you need to stand 60 centimeters away from the center of the room, and you shouldn't be able to hear anything at all from these speakers. So that's 0.60 meters. If I just continue on to do x2, so put 2 in for n, I'm going to get 1.8 meters. So again, that's 1.8 meters away from the center line, and blah, 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 keep going on. You should be getting more and more of these spots. And this is how far away you have to stand from the speaker in order to not hear it. And if you're somewhere in between these, you should be able to hear it, and about halfway through, it should be about twice as loud as a single speaker would be. So that's hopefully you got that, and that's it out of me for today. I know it was a little bit longer than it normally is, and I apologize for that, but I think this hopefully should be pretty good for you guys. And if you have any questions, let me know, and I'll see everybody in class tomorrow.